The focus of this unit is what we call equilibrium calculations, which is the math that is involved in the equilibrium unit. And this is going to take several different forms. We're going to be talking about the reaction quotient Q, which you can use to determine if a system is at equilibrium or not. And then we'll also talk about what you call ice tables, which is a more in-depth look of doing calculations that involve equilibrium. So the first thing I'm going to talk about is Q, which is known as the reaction quotient. I'm going to underline that as opposed to K. And you're going to be doing a program on this sometime the next few class periods. So this is a good introduction to talking about what exactly Q is, and then hopefully the program can give you some more in-depth look at what it is. Okay, now if you look at the expression right here, the Q expression is it's indicated as once again the product over the reactant, and the coefficients in the equation become the exponents in the Q reaction quotient. And this is very, very similar to the equilibrium expression, but there is one specific difference about when you use Q. And that is you use Q if you are not sure whether the conditions are at equilibrium or not. And we use Q, the reaction quotient, to determine what the direction of the reaction is going to be to get to equilibrium if it's not at equilibrium. So we're taking a look at this, and these are equilibrium concentrations or concentration at a given moment if it's not at equilibrium. If Q, which is the current condition, equals K, which is equilibrium, then that means the system is at equilibrium. So if Q is less than K, and remember that Q, just like K, is product over reactant. So if Q is less than K, which means Q is too small, that means that we have to increase the numerator, which in this case would be the product. So that means that the forward reaction, the equilibrium is the equation, the reaction mixture is gonna make more product until the equilibrium has been reached. Now, on the other hand, if Q is greater than K, which means that Q is too high, that means that, conversely, we need to make Q smaller, so we have to increase the denominator and make more reaction. So that's why we're saying here that the reverse reaction will occur until the system has reached equilibrium. So what I want to really emphasize with you is that you use Q if you are not sure if the conditions are at equilibrium. So let's put that into play in this particular problem right here. Okay, and let's take a moment to read the problem. So pause the video and read the problem. Okay, so the question specifically asks if it is not at equilibrium, indicate the direction in which the mixture must shift to achieve equilibrium. And notice here that it is giving you KP. So we're going to use Q. I don't need to call it QP, but you should know that since it's KP we're comparing it with, we're going to say that QP, Q equals the pressure of the NH3 squared over the pressure of N2, and then the pressure of H2 to the third power. Okay, we do not know, it never says that these numbers are equilibrium values, equilibrium pressures. We just know that they are representing the current condition. So we're going to go ahead and substitute those numbers in. Q equals 105. You don't need to include the unit, by the way, because K and Q have no units attached to it. So I can go ahead and this is one of those cases when you can ignore the unit. 495 to the third power. And go and put that in your calculator. and see what you get. And I got a value of 2.6 times 10 to the negative 6. And let's compare that value of Q to the value of Kp. And you notice that Q is less than Kp. So the system, we can say therefore, system not at equilibrium. And I said in the earlier slide, because if Q is too low and you want to increase its value so that it reaches the value of K, you would need to increase the numerator, which would mean that more products will form. Until equilibrium has been reached. Okay, and that would be a nice complete answer. And just you can't say I didn't warn you here, but expect to see this on a future free response assessment. And you heard of me here. Yeah. All right. So once we have that, we can go ahead and move on to the other major topic of equilibrium, and that would be what we call ice tables. And you're going to see ice tables as a variation of the stoichiometry limiting reaction tables that had to do with the before the reaction, the change, and the after the reaction. And we use the ice tables, which you're going to see in a second, to calculate what the value of K is, the equilibrium constant, or if you're given the equilibrium constant K, how to find like the initial concentration or equilibrium concentration, etc., depending on what the situation they're calling for. So let's take a look at a sample problem right here. Calculating Ka for this HF solution if at equilibrium, the H plus is 8.13 times 10 to the negative 3 molar. And we're going to talk a bit more in the acid-base unit about what Ka is, but just think of this as a variation of the K equilibrium constant, except it deals with acids and bases, in this case specifically the equilibrium involving the acid. And this is just a sample problem of how this happened. Okay, but the equilibrium equation will be HF acid aqueous is going to dissociate into H plus AQ plus F negative AQ. And based on that, the equilibrium equation will be, of course, the products over the reactant. And we're going to go ahead and use this information for the ice table that's coming on right up here. Right here, the initial concentration, it tells you that the value at equilibrium, the value of H plus, is 8.13 times 10 to the negative 3. Slide initially asks you to calculate what the value of Ka is. So that, okay, and we create a summary table to determine the concentration at equilibrium and then solve it. Okay, so once again, I'm going to go ahead and rewrite that equilibrium expression right here and figure out what exactly we are trying to solve. Okay, so what exactly is an ice table? Well, it refers to the fact that you have I, which is the initial condition, then this is delta, which means the change, and then equilibrium, ICE. Very similar to before the reaction, the change, and the after reaction. Now, if we look at the preceding slide of HF, before it dissociated, is 0.100, and this hasn't quite broken up yet, so we're going to make these concentrations 0 and 0. Okay. Now, the question specific, so we're going to put that right here, 8.13 times 10 to the negative 3. So the change, this had to be plus 8.13 times 10 to the negative 3. And because this is a 1-to-1 ratio, this would also be increasing by the same factor of 8.13 times 10 to the negative 3. And again, because of the 1-to-1 ratio, this will go down by 8.13 times 10 to the negative 3. Okay, and you can, if you need to, put this in the calculator, but I'm just going to go ahead and write it all out. And the question we're trying to find out what the Ka is. So we're going to substitute all of these numbers in the equilibrium line for the concentration to find out specifically what Ka is. So Ka equals 8.13 times 10 to the negative 3. F negative is also the same thing. And then the HF is the 0.1 minus 8.13 times 10 to the negative 3. And go ahead and pause the video and put this in your calculator to see what number you come up with. And I got 7.19 times 10 to the negative 4. And that, notice, I do want you to notice that equilibrium constant is much less than 1, which means that the reactant, the HF, is highly favored. And that would make sense because this is a weak acid, which means that it does not break up very much in solution. Okay, so that's one example of how you might use an ice table. So let's go ahead and look at this. Another example here. When you do ice tables, you must make sure that you only use molarity or pressure, usually ATM, but it could be other pressure unit. You can't use mole, and you can't use gram when you do the ice table. Okay, now before the reaction, the change, and after reaction that we did for stoichiometry, you use moles. But this one is specifically molarity and pressure unit. Okay, so let's look at this sample problem. So pause the video and read through this. Okay, so let's look at the problem right here, the ice table that goes along with it. So the first thing I told you is that when you use the ice tables, you have to use molarities and not moles. Bearing in mind the formula for molarity is moles divided by the number of liters. So when you look at this problem here, it says that there's 0.2 moles of CO in 2 liters. So that means that the CO concentration equals 0.20 moles over 2 liters. And that's going to be 0.10 molarity. And that's going to be the same thing for the H2O as well. 0.100 molarity. So we put both of those into the ice table. And it says nothing about any CO2 or H2 being added. I'm going to put 0 here and 0 here. And we only know the value of Kc in the end other than the initial concentration. So we're going to go ahead and make an equilibrium expression. Okay, so that would be Kc equals CO2 H2 over CO and H2O. Okay, so we don't know how much this is going to go up and down by, so we're going to go ahead and say that this is going to go up by a factor of x. And again, because of the 1-to-1 ratio, these all go down by minus x. So that's 0.100 minus x. And then that would be x and x. And based on the information we have, we can put x in for both CO2 and H2. So that numerator will become x2. In the denominator, since the 0.1 minus x are both identical, and you can say squared, and that's going to equal the Kc value that's given to you in the problem of 4.06. And at this point, you can actually use your graphing calculator where you can plug the left side in the calculator under y1 and the right side under y2 and determine where the two of them intersect with each other. Or you can square root both sides. As long as you allow the calculator, you can use whatever method that suits you best. So go ahead and pause the video and solve for that value of x. So you should have gotten two possible answers that x could equal 0.0668 or 0.199, but it can't be 0.199 because if you do 0.1 minus 0.199 right here, you're going to end up getting a negative concentration, and that's not possible. So I'm going to go ahead and cross off this one, and we can say the value of x is 0.0668. So that leads us to conclude that the concentration of CO2 at equilibrium will be 0.0668 molar, and that's also going to be the concentration of hydrogen, and then the concentration of CO and H2O, which will be the same, will be 0.1 minus 0.0668, which is 0.0332 molar. And that answer would make sense because if you look at the value of Kc, that indicates that products are more heavily favored. And based on the one-to-one reaction, stoichiometry of the coefficient, if you look at the molarities, it seems to imply that the products are favored to a greater extent than the reactions are. Okay, so we're going to get a chance to practice some more ice tables, but these are like the easier ones. So you'll have your hand at trying some of the more challenging ones like you might see on the AP exam or the college level chemistry class. But I definitely encourage you to be resourceful, knowing how to use your calculator to solve the complicated quadratic style equations. And I probably won't require for you to do them on a test, but you might still find it useful, especially if you're running low on time, to be able to solve these questions by using your graphing calculator. Okay, so that's it for this lecture.